Hey everybody, welcome back. It's Mr. G here again. Today we're going to be doing the next in the lecture series for ELIC 200 electric machines. And what we're going to be looking at today is magnetics and how it causes motor movement. So we know from previous lectures that magnetics, you can have like poles are going to repel, opposite poles are going to attract, and that's all based on the theory that we had talked about before, where Michael Faraday had said that we look at the magnetic principles as magnetic lines of force, and they have certain characteristics. We also looked at the thought that magnetics is a field force, so the ability to cause movement without physically touching something. So if we looked at our little magnets that we have opposites, they're going to attract. If we have like poles, they're going to repel. So basically, if I was to move this magnet closer to this one, it would cause this one to move away. So move this one closer, this one will continue to move. And basically what happens is, if we can control one magnet, we can actually cause the other one to move. So it's kind of like this magnet is chasing this magnet. If we did the same with the North Poles, the same thing would happen. If I move this magnet, again, what's going to happen is the other magnet will continue to run away. So that's the basis of what we're going to be talking about. We're going to be looking at how magnetic fields are causing movements. And when we look at a motor is a machine that moves, so we end up with mechanical movement. So if we looked at a motor by definition, a motor is a machine that converts electrical energy into mechanical energy. Again, a motor is a machine that converts electrical energy into mechanical energy. So, how is that all done? Well, it's done through magnetics. Where does the electrical part come in? Well, we don't have to have a permanent magnet. We can have an electromagnet. So if you remember our discussion from the last video about solenoids, and we had looked at our right-hand rule for conductors and our right-hand rule for solenoids. If you can't remember, go back and watch that video again. So if we took a permanent magnet and an electromagnet, and I energized that electromagnet and I moved it, it would cause the permanent magnet to move. So it's just the same as two permanent magnets. Now we have one that's an electromagnet. Now remember, if I was to move this one would run away. So we're looking at the interaction of the magnetic lines of force. So what would happen if I got rid of this and I took a conductor and I put current through the conductor? If you remember from our discussion, our right-hand rule for conductors said if we put our thumb in the direction of conventional current as it flows through the conductor, our fingers wrap around in the direction of the magnetic lines of force. So the magnetic field wraps around the conductor like this. So if I have a magnetic field So from this permanent magnet, I have a magnetic field. And then I have a magnetic field that's created around this wire. It would have the same principle as this and the same principle as this. So again, as long as there's an interaction between two magnetic fields, we can cause movement. So in this case, it's two permanent magnets. In this case, it's one permanent magnet and one solenoid or electromagnet. Or in this case, it is one permanent magnet and one conductor. So what we have to come up with is we have to be able to figure out how this conductor moves when it interacts with a magnetic field. And that ends up being the majority of our discussion today, is looking at how a current carrying conductor, when it comes into contact with a magnetic field, how does this move? So what I have here is an example of a motor. We have north and south poles of a magnet. So a magnetic field, as we know, the magnetic lines of force pose direction, and the direction is from north to south. So there's a magnetic field that's flowing in this direction. I now place a current carrying conductor in a loop. I place it inside the magnetic field. What's going to happen is once current is put onto this conductor, it is placed inside the magnetic field. The magnetic field from the permanent magnet reacts with the magnetic field that's going around that wire, and this wire will move. The question becomes, which direction does it move? So, just for this example, we will say that this is the positive. So that means current, conventional current, is going in the wire this way, and it's making its way around and coming out over here. So basically what we have is a loop of wire. So what we need to do is we need to examine each wire or each part of the loop separately. So what we're going to do is we're going to examine this part of the loop, and then we're going to examine this part of the loop. And that'll determine which direction that wire will actually move. And what's going to happen is it will rotate. So the movement will be in a rotating fashion. And that gives us our movement, or our mechanical rotation of a motor. So what we have, again, is a conductor forming a loop. We're going to put current in the conductor, and we're going to place that conductor inside a magnetic field. What we need to do is figure out how this moves. So to do that, we have to look at a rule. And the rule is what's known as the Fleming left-hand rule for motors. So far we've got two right-hand rules. We've got the right-hand rule for conductors, which states that if you put conventional current through a conductor and you put your thumb pointing in the direction of conventional current flow, the magnetic lines of force, as they wrap around that conductor, will wrap around in the direction of your fingers. Then we had the right-hand rule for solenoids. Right-hand rule for solenoids says that if you wrap your fingers around in the direction of conventional current flow, your thumb points to the North Pole. So that is two laws so far, two rules. The third one is what's known as Fleming's left-hand rule for motors. So what that means is you take your left hand and you make this shape. So you have three dimensions. Okay, so three different directions. So you take your finger and you have this shape. Okay? This finger here represents the direction of the magnetic lines of force, so the direction of the magnetic field. This finger represents the direction of conventional current as it would flow through the conductor. Your thumb then represents the direction or the resulting direction of movement of the conductor through the magnetic field. So again, your index finger represents the direction of the magnetic lines of force, or the direction of the magnetic fields from north to south. Your middle finger represents the direction of conventional current as it flows through a conductor that is inside that magnetic field. Your thumb then represents the resulting direction of the movement of this conductor through the magnetic field. So the idea is, if I was to have a magnetic field from north to south, and I took a current carrying conductor, I'll just get a smaller one here. So I took a current carrying conductor and I placed it in that magnetic field. Okay? Which direction would the conductor move? Now, the hint is it will move out of the magnetic field. So that means it will either move this way or it will move this way out of the magnetic field. Your left-hand rule, Fleming's left-hand rule for motors, will determine which way this conductor actually moves. So, my index finger points in the direction of magnetic lines of force from north to south. If in this conductor the current is coming out of the table, the conductor will move through the magnetic field in the direction of your thumb. So if the conductor has current that's coming out of the table, it will move this way. If the current is going into the table, the conductor will move this way. So let me just modify this a little bit. I'm going to grab myself a conductor. So there's a conductor. And if you remember, that notation means that the current is going into the table. And I'll grab another one. This notation means current's coming out of the table. So let's go with this one first. So I place a current carrying conductor inside a magnetic field. The magnetic field that's created around that conductor will interact with this magnetic field, causing the movement of this conductor. The question will be, what direction does it move? That's where this rule comes in. So again, Fleming's left-hand rule for motors states that if you place your index finger in the direction of the magnetic lines of force, so from north to south, if you put your index finger in the direction of current, so current is going into the board or into the table this time, your thumb points in the direction of the resulting movement of that conductor. So this conductor will move out of the magnetic field in this direction. If I swap the direction of current, again, index finger north to south. Current is now coming out of the board. My thumb points in the direction of resulting movement of that conductor. So my thumb points in the direction that this conductor will move this way out of the magnetic field. So we have what's known as Fleming's left-hand rule for motors. Fleming's left-hand rule for motors. If you have the direction of the magnetic lines of force and you have the direction of the current in the conductor, the rule will show you the direction of the movement of that conductor. So in your class notes, you have this diagram. So again, there is your Fleming's left hand. This one points in the direction of the magnetic lines of force or magnetic field. This one points in the direction of conventional current flow. And your thumb is the resulting direction of movement of the conductor. So again, if we place a current carrying conductor inside a magnetic field, the conductor will move. It will move up or down depending on the direction of the current. So again, you have that in your class notes. So let's go back to this example. So I have a current carrying conductor inside a magnetic field. I'm going to focus on this part of the conductor here. So I have my left-hand rule for motors. My index finger points in the direction north to south of the magnetic lines of force. Current is actually going into the paper, so it's coming in and flowing through. So current is actually going in like this. This conductor here will actually move down. So this conductor will move down. Let's go over here and look at this conductor. Again, direction of magnetic lines of force. The current is now coming out. Current coming out. This part of the loop is going to move up. So this part is going to move up. So what we have is actually a rotational force where this part is moving down and this part is moving up. So now we have rotation. So if we look at this from a very instantaneous point of view, and I took a snapshot, boom, I froze the picture. We can see that this side of that loop is going up, this side of the loop is going down, and again we determined that from Fleming's left-hand rule for motors. That side's going up, that side's going down. So the general rotation of this loop inside this magnetic field is going this way. Okay, so general rotation this way. Okay, so what if we changed the direction of current? So I now make this the positive and current is now going in this way and coming out here. So again, we're going to rely on Fleming's left-hand rule for motors. Magnetic field. We're going to concentrate on this wire. Current is going into the paper. This wire is going to move down. As the loop comes all the way around, magnetic field, current is now coming out over on this side. That part of the loop is going up. I will bring back our first example. In this case, this part was going down, this part was going up, and we were going in a counterclockwise rotation. In this, that same side is now going up, this one here is going down, and now we are going in a clockwise rotation. So we can then make the conclusion that the direction of rotation is determined by the direction of the current as it flows through the loop. So if you were to change the direction of the current through the loop, you could therefore change the direction of a rotation of a basic motor. So I'm just going to take this is example 2, move it out of the way. I'm going to bring in another example. In this example, I'm going to keep current the same. But now what I'm going to do is I'm going to swap the poles of the magnetic field. I'm going to make this the south and this the north. Notice the current remains the same, but I'm now swapping north and south poles. So we're going to use our Flemings left-hand rule for motors again, north to south. Let's concentrate on this wire going in. Thumb is pointing upwards. So this part of the loop is going up, north to south, current coming out of the board. So again, I've got to be a contortionist to do this. And my thumb is pointing down. I will bring back example 1. In this case, I'm going counterclockwise. I swap the polarity of the magnet, and now I'm going clockwise. So we can conclude that if we were to swap the magnetic lines of force, the direction, so the polarity of the magnet, it will also change the direction of rotation of a basic motor. So, if we were to change the current direction and leave the magnetic field the same, the direction of rotation changes. If we were to leave the current the same and change the direction of the polarity of that magnet, we change the direction of rotation. All right, so on the left side, I have a DC motor, and on the right, I have a basic AC motor. What we're looking at is a loop inside a magnetic field. A loop inside the magnetic field. You will see that the internal parts of an AC motor and a basic DC motor are theoretically the same. The difference is in the outside of the motor. In the DC, we have what's known as a commutator and some brushes. And I'll explain the purpose of the brushes in a minute. So we've got a commutator and brushes. With the AC, we have 2 slip rings and brushes. So the internal parts of the motors are the same. It's how do we feed the electricity in is different in each style. The DC, we have what's known as a commutator. So it's 1 ring and it's split. And then we have 2 brushes. With the AC, we have 2 separate rings, we call them slip rings, and 2 brushes. Because we know that DC is current in one direction and one direction only, the job of the commutator is to actually help change the direction of current inside the loop. AC, we have a nice sine wave where current is going in both directions, so one direction and then another direction. when fed directly into the loop, we actually change the direction of current in the coil when it's time to actually go to the other side. So to continue our direction of rotation, the current must change. Here, it changes naturally with an AC. Here, we have to fake it with what's known as a commutator. So the commutator actually switches the direction of the current as rotation happens. Okay, so what is the job of the slip rings, of the commutator, of the brushes? Well, what I have here is a motor, just a simple DC motor. I know it's a DC motor because it has a commutator. So that little brass part there is a commutator. So it's one ring broken into a bunch of different parts. The brushes are actually on this motor right here. So what I'm going to try and do is I'm going to try and get a closer picture for you in a moment. So we have two wires that come from the outside world, and their job is to feed electricity into the winding, or that little coil that we had in the previous picture. And then it rotates between two permanent magnets. So there's one here, that's one permanent magnet, and here's the other one on this side. So basically we've got a coil of wire, and it's inside, in between the permanent magnets. So magnetic field is being created, and we're actually causing rotation. Now, I need to feed electricity into this coil to create the magnetic field around the wire so that it interacts with the permanent magnetic field to cause the movement. So if I just took two wires, here's one, and here's another, and I just fed the electricity in like this. So this is going off to a power supply somewhere, and then I started putting current in the wires, and this thing started to rotate. Watch what's going to happen. What's happening to the wires? Okay, as this thing starts to rotate around, the wires are wrapping around each other. So let me see if I can actually do this and make a real better example for you here. So let's say I plug this wire in like that, and I plug this wire in like that, and they're coming from my power supply. When electricity hits, here's what happens. This thing starts to rotate. Okay, so as this rotates, and it's hard to do because I'm holding it. There we go. So as this thing starts to rotate, the wires themselves get twisted amongst each other, and then they break off. So as this thing starts to rotate, the wires that are getting the electricity in from the outside world actually start to twist amongst each other. And what happens is, what just happened there is it breaks off. So we have to somehow get the electricity inside that coil. But once it starts to rotate, we have to make sure that the wires just don't twist amongst each other and break like we had here. So that's where the brushes come in. Here is a full-size brush from a larger motor. Basically, it is a soft carbon material. We have a spring, so it is spring loaded, and you'll see that there is a wire that actually runs through the spring to this metal plate. So let me just put a white background so you can see a little better. Okay? So what happens is let's pretend that this is the slip ring. So what happens is electricity from the outside world is fed to this plate here. Again, this is spring-loaded. The slip ring is connected to the wires inside the motor. So the slip ring actually rotates with the motor. The brush sits against it, spring-loaded, feeds the electricity in through the brush to this ring. The ring is allowed to rotate with the motor, but notice how the brush does not move. So the ring is allowed to rotate as the motor spins, keeping a constant pressure with the spring, so electricity is being fed from this end, through the spring, through the brush, to the slip ring. So the slip ring can spin, and the wires outside stay in one location and don't get twisted. When it's a DC motor, instead of a slip ring, we have a commutator. So think of it as one ring broken into two sections. So something like this. So the ring is on this side of the commutator, and then when the commutator slips around, the brush is on this side. As the commutator flips around, the brush goes to the other side. So the commutator rotates, again the brush stays in place. So the job of the brush and slip rings or commutator is to be able to bring electricity from the outside world into a rotating machine without twisting the wires around. Okay, so again, the job of the brush and slip rings or commutator is to bring outside electricity into a rotating machine without spinning and twisting up the wires. So that's the job of the brush. And in an AC, we have slip rings. In a DC, we have a commutator. So I'm going to see if I can zoom in on the camera a little bit and get you an idea of what it looks like in this small little motor. Alright, so real close. This is the commutator of this DC motor. Again, there's the magnet, so there's one side of the magnet, the other side of the magnet, just like our drawing. The commutator, you can see, is split up into many little pieces. Here are the brushes. So basically, electricity comes from the blue wire, gets connected here permanently, follows this wire around to this brush. The red wire comes in over here to this brush. So these brushes are spring-loaded. Okay, so they're spring-loaded. And what happens is, when this goes on, it sits on the commutator. And I'll see if I can show you this as I'm doing it. It's hard to keep it in focus. But basically these brushes spread out. And the commutator fits in between. Like so. There we go. Okay, so now you can see the commutator is now spinning inside the brushes. So the wires themselves don't move. So this is off to the outside world. So the electricity is brought to the brush, and then from the brush into the commutator. So as the commutator spins, or as the motor is spinning with the commutator, the brushes allow the motor to spin without twisting the wires from the real world. And again, when I separate this is what happens. Watch, the brushes will spring loaded, they'll pop back into place. There we go. And flip them over. So again, the brushes themselves, okay, so the brushes themselves are spring loaded and they touch up against the side of the commutator and bring electricity from the outside world to the inside world of the motor. If this was an AC motor, the brushes would be the same. We would just have two completely separate rings. As opposed to one ring split up, we will actually have two completely separate rings, and each brush would permanently touch one ring. So the difference between an AC and a DC motor in its basic form is that an AC motor has brushes and slip rings, whereas a DC motor has brushes and a commutator. And a commutator is one ring that is split up into a bunch of little sections. This is what the other larger brush looks like. So this one is from a much larger motor. Again, it's made out of a soft carbon material. Normally the slip rings and commutator are like a brass material. They're very hard, so that the brush actually wears out, and these are replaceable. Okay, so you can actually replace these when they wear out. So the electricity from the outside world will be here. It goes through this wire inside the spring to the brush, and then from the brush to the slip ring. And the slip ring is allowed to rotate against that brush. All right, so what we have for today's lesson, we have Fleming's left-hand rule for motors. Again, when you have a given magnetic field and you know the direction of conventional current flow, you can determine the resulting direction of movement of a conductor through a magnetic field. When we look at it as terms of a loop inside a motor, we can determine which direction the motor is spinning. Again, based on the direction of magnetic lines of force, the direction of current, and therefore the direction of movement. So in this particular case, we're going to get a clockwise. If we swap the direction of current, we're going to get counterclockwise. And if we swap the direction of magnetic field, again, we get clockwise. The differences between AC and DC, so at the basic form, inside, they are the same machine. How the electricity gets in, with an AC, it's with brushes and slip rings. DC, it's brushes and a commutator. And again, the job of the commutator is to swap the polarity upon rotation. Well, I hope this helps. Until next time, everybody stay safe. Take care.